Hello grade 11s. Welcome back to our next lesson. So we're just going to continue with the exercise, I believe it was 24 on page 129. So I'd given you question number 7 until question number 14 for homework. Just some basic calculations that you had to do. So let's have a look. So it says a light bulb is plugged into a 220 volt outlet, so you have voltage, it has a current of 0.7 amps. What is the power? Okay, so that one's nice and easy. You have an equation, P is equal to IV. So you would have 0.7 multiplied by 220, which would have given you 154 watts. Okay, don't forget the unit. Okay, then it says a calculator uses 4 1.5 volt batteries connected in series and has a power rating of 80 microwatts. What is the resistance? Okay, so when we read this question, we notice that we have firstly voltage, which is going to be 4 1.5 volt batteries. So if there's 4 batteries and each one has 1.5 volts, then we'll know that that's 6 volts. And we know that the power rating is 80 microwatts. Okay, so micro is one of the conversions that you have to know. Okay, micro would be times 10 to the negative 6. So then this would be 80 times 10 to the negative 6 watts. Okay, so let's have a look. So our equation that we can use, they said they want to know what is the resistance. Okay, so if we look at the equations that we went through last time, we need to obviously pick up power, voltage, and resistance. Okay, so that is P is equal to V squared over R. Okay, they want to know what the resistance is. So therefore the resistance is equal to V squared divided by P, which is going to be the 6 volts squared divided by the power, which is 80 times 10 to the negative 6, which is going to give us an answer of 450,000 ohms. Okay, then the next one, it says a 25 ohm resistor, so we have resistance, has a potential difference of 12 volts. V, calculate the power. So again, we're going to say that the power is equal to V squared over R. The voltage is 12 squared over the resistance, which is 25, and then we'll get an answer of 5.76 watts. Okay, so the next question, it says a dishwasher has a resistance of 550 ohms. It has 1.3 amps of current flowing through it. To calculate the power used. Okay, so we have an equation that power is equal to I squared times R. The I is 1.35 squared multiplied by 550 ohms, which is going to be equal to 1002.38 watts. Okay, so moving on. It says an electrical appliance is marked as 2,500 watts. So we have power, which is 2,500. We have current, which is 1.5. So it says calculate the resistance. So again, we're going to use this formula that we used above. So we're going to say power is equal to I squared times R, which means that R is equal to P divided by I squared, which is 2,500 over 1.5 squared, which is going to give you an answer of 1,111,11 ohms. Okay, and what voltage should this appliance operate? Okay, so we can use our power is equal to I times V. You can use any formula based on the information that we have. I'm just using P is equal to I times V because we've been given the current and the power, so it will be better to use this equation just in case this one had to be wrong. So therefore the voltage is equal to the power over the current, which is going to be equal to 2,500 divided by 1.5, which is going to be equal to 1,666,67 volts. Okay, number 12 says a microwave oven is plugged into a 220 volt socket with a current of 1.5 amps flowing through it for 3 minutes. Okay, so we have time, which I'm going to already put here is 180 seconds. Calculate how much energy W is converted inside the microwave oven. Okay, so for this one, you can just use one of your energy equations. Okay, there is one where you're using both VI and delta T. So you'll say, well, work is equal to V times I times delta T. So that means that the voltage is 220, the current is 1.5, and the time is going to be 180. So if you multiply all of that together, we'll get 59,400 joules. Don't forget the unit again. Okay. Then number 13, it says a lamp has a resistance of 50 ohms. It uses 1,450 kilojoules of energy for 2 hours, so time. So 2 hours, you'd multiply by 60 to get minutes, and then 60 again to get seconds. So it's for 7,200 seconds. Calculate the amount of charge, Q, that flows through the lamp at this time. Okay, so if we noticed none of the equations for power or for work give us the charge of Q, will give us Q, right? We look at rather the Q from our original definition for current. Okay, so what we can do is we can first calculate the current, and then we can use Q is equal to the current multiplied by the time. So the equation we can use is W is equal to I squared times R times T. So we know that the work is, now be careful, it's kilojoules and not just joules. So it would be 1,450,000 joules of energy. Please don't forget to convert. Okay, it's very important. I'm going to make a little highlight here that it's kilojoules. I squared times R, which is 50 ohms, times the time, which is 7,200 seconds. So we'll put that all in the calculator, and we'll get I is equal to 2.01 amps. Then we can take that current and we can put in this equation and say, well, 2.01 amps multiplied by 7,200 seconds is going to be equal to 14,449.91 coulombs. Okay, don't forget the unit. Okay, then number 14 says a generator generates 5 megajoules per minute. Okay, so megajoules of energy is just going to be 5 million joules. Okay, so we don't megajoules and the gigajoules and those things, it's not really something that we would give too often, but definitely when we were doing kilojoules and micro and those things are very common. Okay, so don't just get confused when you see this. Okay, it's just 5 times 10 to the power of 6. Okay, that's mega. So the resistance of the generator is 12 kilo ohms. Okay, so that's 12 times 10 to the 3. Determine the induced EMF, which is obviously going to be the voltage. Okay, so we are given the work and we're told it's per minute, so we're told that the time is per minute, which is 60 seconds. Okay, we are given R and we want V, so we can use our equation that says, well, work is equal to V squared times time over R. Okay, we know that work is 5 times 10 to the 6, which is equal to the voltage, which we're trying to find, multiplied by 60, all divided by the resistance, which is 12 times 10 to the 3. Okay, so if we put that, we do some maths, we'll get our voltage to be equal to 31,622,78 volts. Okay, so that essentially marks the end of our corrections that we did. So if you need to go over some of the questions, if you need to redo them, if you completely misunderstood, then I suggest you go over them again. But otherwise, we're going to move on to the next topic. So these questions are going to be based on more combination circuits, but now we're going to look at what happens when we use these combination circuits as well as power calculations as well. So we need to look at now a combination of both of them. So these are kind of like the most advanced kind of questions in a way that you're going to be asked besides the exam questions. Okay, so you can put somewhere the date, which is going to be the 12th of May. And we're just looking at combination circuits again, but this time that includes power as well. So it's just still power calculations, but now we're just going to look at some more advanced things. Okay, so let's start at number 15.1 in the same exercise that we've been busy with. It says, show how 3 identical 6 ohm resistors must be connected to have the following effective resistance values. So it's 9 ohms and 4 ohms. So if you had 3 resistors of 6 ohms each, so you have 6 ohm resistors, 3 of them, you need to figure out how are you going to arrange those 3 resistors in order to give you this total resistance in the circuit, and then this one. So take a moment. Okay, this is very important. Pause the video and try and figure out exactly how these resistors are going to be arranged, and then unpause, and then we can go over it. So just think about it carefully, and then we can look at it together. Okay, so if we look 6 ohm resistor, first of all, we can't put them all together. So if I'm going to, in series, put them all like this, then I know, okay, well, that won't work because 6 plus 6 plus 6 is going to be 18 ohms. So that doesn't work. Okay, so series won't work for either of them. And then if we do parallel, then we would say, oh, but this is 1 over 6 plus 1 over 6 plus 1 over 6 to the power of negative 1. So if we do that, you get 2 ohms, which also isn't one of these two. Okay, so now you have to think, okay, if it's not series and it's not parallel, then it must be a combination of these circuits. Okay, so let's first try, well, if I had one in series and the other two in parallel, then what would I get? So if I did this, I would say, okay, well, I'm just going to put R, but we know that R is 6 ohms. So let's have a look and see. If I have 6 plus 1 over 6 plus 1 over 6 to the power of negative 1, okay, because remember this is the parallel part added to the series. So if you put that on your calculator, so 1 over 6 plus 1 over 6 to the power of negative 1 is 3. So 6 plus 3 is 9. Okay, so there's the first one. Okay, you can't guess this. Okay, it has to be something that you calculate. Okay, so let's look at the 4 ohm one. So we've already tried now all three in parallel. We've tried all three in series, and now we've done one in series and the other two in parallel. Now, what would happen? The only other option now is to take the parallel component and to put the series within the parallel. So what that means is, it means we'll try to look at it by saying, okay, I have two in series, but they must be in parallel to this. So that's really all the types of combinations that we can do. All three in series, all three in parallel, one in series, two in parallel, or two in parallel and then the other one in parallel as well. So let's see how this works. So firstly, I would have to calculate the series part of the component. So I would say, okay, well, if this is 6 plus 6, then this part would be 12 ohms. And this would be 6 ohms. So if I said 1 over 12 plus 1 over 6 to the power of negative 1, 1 over 12 plus 1 over 6 to the power of negative 1, you would get 4 ohms. Okay, so there we go. That would be your two circuits. You'd have one that looks like this and the other one that looks like that. Okay, so it says in 5.9.1, the combination is connected to the terminals of a battery with an EMF of 12 volts. So you were told what the voltage is here. And negligible internal resistance. Okay, they want to know what the current is through each resistor. Okay, so it's important to note that the current is obviously going to be different for the resistor in series and the resistors that are in parallel with one another. Okay, so what we do know is that this resistor that's in series is going to get the current that is the total current. Okay, so we know that for a fact. So that means that we can calculate the total current through the circuit, which is going to be equal to V total over R total. Okay, so the V total that goes through is going to be 12, and the R total is 9. The reason why I didn't use 6 here by this 9 is because we don't know that 12, it's impossible for 12 volts to go through this resistor only, because then there would be no more voltage left. Remember, they said the total voltage is 12. So it means the voltage here plus the voltage here is equal to 12. So that's why I didn't use 6 here, because it's not 12 that goes through the 6, but it's rather 12 that goes through the whole resistance, the total resistance. Okay, so then I get an answer of 1.33 amps. Okay, so that would be, let's call this R1, R2, R3, and we'll also do R1, R2, R3. So R1 is going to have a current of 1.33 amps. Then R2 and R3 are going to have the same current because they have the same resistance. So because this is 6 and that's 6, all I have to do is then I take the total current, which is going to be 1.33, and divide by 2, which is going to be equal to 0.667 amps. So R2 and R3 have a current of 0.67 amps each. Okay, then it says, what is the potential difference across each resistor? Okay, so we need R1, R2, and R3. Okay, so now we know the current through R1. So we can calculate the V, which is I times R. So the V through resistor 1 will be 1.33 amps multiplied by the resistance, which is 6. And then I would get an answer of 8 volts. Okay, so that's the voltage through resistor 1. Then if I look now at the resistor 2 and 3, first of all, resistor 2 and 3 have the same voltage again, okay? And that's not because they are the same resistance, it's because they are in parallel. So the voltage here is the same as the voltage here. So you can calculate, now you know the current, so you can calculate the voltage that goes through it. However, it's also, you can also just minus from the total voltage, so it's up to you. So there's two methods here that you can use. The first method is to calculate the voltage through the resistor each. So you would say, well, V is equal to I times R. The current is 0.67 multiplied by the resistance, which is 6, and you get an answer of 0.67 times 6. You would get an answer of 4.02. Okay, it's important to remember that this answer is rounded off. So if you actually use the unrounded off answer for this one, because it's not 0.67 but it's 0.6666, and so it continues. So if you did that, you would see you actually get 3.9999. So it actually should be equal to 4 volts. Okay, and remember that's if you use this one, let me highlight it for you. This one, try and make sure that you use the original value, so before rounding. Okay, that's why the other method might be a bit easier. So the second method is that we already know what the EMF is. They said that the EMF was 12. So technically the V through the parallel would equal to the EMF minus the V through the 6 ohm that's in series. So I would say, well, that is 12 minus the 8, which is just 4 volts. Okay, so both, you could have used both methods in that case. Okay, then 15.2.3 says, what is the total power in the circuit? Okay, so for total power in the circuit, we're going to use total equations again. So we're going to say, well, P total is equal to I total times V total. Okay, that's the easiest way. So you can also use the R, but in this case, we're just going to use IV. So it will be 12 would be the voltage. Let me put it under the voltage, times the total current is 1.33. So the total power is 16 watts. Okay, then it says, what is the power in each resistor? Okay, so this one now we have to work a little bit differently. So remember that there's the power that goes through each resistor in series and the power through the resistors in parallel. So in series, you can use two equations here. So the first one is to say, well, P is equal to IV. We know that the current that goes through it is 1.33. The voltage is 8. Remember, we calculated the voltage earlier here. Remember to make sure that you pause the video before going through these questions, because you must be able to do this. Okay, I'm obviously explaining it, but it's not something that you must just be copying down, but rather something that you're interacting with. Okay, so the power here, if you put it in your calculator, you will get an answer of 10.67 watts. Okay, I'm going to put the second method where you could have said, well, the power is equal to I squared times R, which is equal to 1.33 squared times 6, which is 10.67 watts. Okay, so that's just an alternative method that you could have used, yeah. Okay, then in parallel, remember the power is going to be the same for each resistor in parallel. So we'll say, well, the power is equal to V squared over R, which is 4 volts each, over the resistance, which is 6. So I get 2.67 watts. Okay, remember you can use any of the equations as long as you get to the right answer, then it's perfectly fine. Okay, so let's read through number 16. It says, can a 1200 watt heater and another 400,000 watt appliance be used simultaneously in a 120 volt circuit if the current has a 15 ampere trip switch? Okay, so a trip switch means that 15 amps is the max current. So if the current had to exceed 15 amps, then the switch trips, meaning that it switches off for safety reasons. So let's start by thinking, okay, well, it says that we want to use a 1200 watt heater and a 400 watt appliance. So that means that the power at the same time. So the total power is 1200 watts plus 400 watts, which is going to be 1600 watts. Okay, so this is how much power I need for this adapter thing to run. Okay, I know that the voltage is going to be a 120 volt circuit. Okay, so I need to figure out, okay, what is the current that this is going to produce? So if current is equal to P over V, because I used P is equal to IV, then I would say, well, then the current is the total power over the total voltage, which is going to be 13.33 amps. Okay, now I see 13.33 is less than the 15 amps. So, therefore, the answer would be yes. It can run simultaneously. Run simultaneously. Okay, because we've calculated that this is, so that would be our reasoning, because 13.3 amps is less than 15 amps, which is what they gave us. Okay, and then we'll do the last one together, which is 17. So it says a 240 volt household, so we're given the voltage. circuit breaker is activated when you have 15 amps of current flowing through it. So again, it's the same like the trip switch. So 15 amps is basically the max current. So it says here that an 800-watt heater, 800-watt heater and a 60 ohm light bulb are connected in parallel in the circuit. Okay, so because we're not really given anything, I would recommend that maybe just draw your heater and your light bulb just so that it's a bit easier for you to visualize. Okay, you don't necessarily have to. I just find that it's a lot easier to visualize something if you have a diagram. Okay, so it says calculate the current in amps that flows through the heater. Okay, so the heater has a power of 800 watts. They said, now remember, because it is parallel, the voltage is equal. So the voltage through this is 240 volts. Now I can calculate the current quite easily by just using my PIV formula. So the power is 800. Let me manipulate the formula first. So I would say P is equal to IV, which means that V is equal to P divided by I. So the power is 800 divided by, sorry, I'm not calculating V, I'm calculating I, sorry. So it would be I, which is equal to P over V. So 800 divided by 240 is going to be 3,33 amps. Then it says calculate the current that flows through the 60 ohm resistor. So I have resistance, which is 60 ohms, and you know that the voltage is the same, 240 volts. So I can calculate current by using Ohm's law. And I can say, well, if V is equal to IR, then I is equal to V over R, which is going to be 240 divided by 60, which is just 4 amps. Then it says calculate the resistance of the heater. So you can use any formula, but I think the easiest one is to just use Ohm's law. So because V is equal to IR, then R is equal to V over I. So we already know it's 240 volts divided by the current was 3.33 amps. So if you put that all together, you would get 72 ohms. Then it says, what is the minimum resistance R, okay, that a device can have if a third apparatus is connected in parallel without tripping the ampere fuse? So if we think about that now, right, the current that this third one would have. So let's think about that. We have the heater, we have the light bulb, and now we have this third resistor that we'll just call R because that's what they said. Now they want to know what is the minimum resistance. So in order for me to figure out the minimum resistance, I have to basically figure out how much current I have left. So if I have a look, I'll see, well, I already know that 0.3 amps goes through the heater and 4 amps goes through the light bulb. So I know that this current here is 3,33 amps, and I know the current through the light bulb is 4 amps, which means I can find what the maximum current is that can go through the resistor. So I'll say, well, the current through resistor R is going to be 15 minus 3.33 minus 4. So that would be 7.67 amps. So this is the current that I basically have left. So if I want to know what the resistance is that a device can have without tripping R, I can say, well, V is equal to IR. So 240 is equal to 7.67 times R, which is going to be 31.3 ohms. Okay, I actually think that this should be more or less, the question actually should have asked you for the maximum resistance, because this 31.3 ohms means that you can't exceed the 31.3 ohms, because then you would need more current that goes through that resistor. Okay, but either way your approach would stay the same. Okay, so that's then from question number 15, number 16, and number 17 that we've done together. So for the rest of your classwork and homework, you're going to complete 18, okay, which is with the circuit here. So make sure you concentrate on the circuit, because it has two switches that are opening and closing. Okay, then number 19, which just focuses on explaining this circuit. Number 20, which also looks at an explanation of this circuit. Number 21, which looks at this circuit here. And then 22 as well, which is just a multiple choice question. Okay, so like I said, you have to practice these questions. So please go over them, go over anything else in the video that you may need help with. But otherwise, then, yeah, that's it. Then we can go over corrections, and then we'll go over the last topic in power. Okay, so I hope that it's all making sense. I hope that the video lessons are helpful and that you are keeping with it. And I will see you then on the next one.